Hello, we are ECE Senior Design Team 2020.
Our project was the electromagnetic expulsion of an underwater payload.
This was a project for the Naval Undersea Warfare Center located in Newport, Rhode Island.
I'm Alex Podgorski.
I'm Alex Polakis.
And I'm Joseph Slavinsky.
Our project provides research alternatives for traditional methods of deploying payloads into the sea from a submerged platform. Recent advances in unmanned underwater vehicle technology have increased the number of different payloads the U.S. Navy is interested in deploying. Traditional methods utilize a hydropneumatic ram to pressurize water for launches. Our method develops the potential for launch with electromagnetic forces, substantially reducing the number of moving parts. The launcher is designed to be able to load the payload from a dry space. This allows personnel the required amount of access. The watertight hatches provide a boundary between the inhabited dry space and the open ocean. During launches, the interior of the chamber will be flooded and subject to the extreme pressures of the deep ocean, requiring a strong metal construction in order to maintain its structure. A small, solid iron slug is placed behind the payload, interacting with the magnetic field to push the payload out.
The energy for launch is stored in a high-voltage capacitor bank. There are 3 stages on our launcher, each with individual energy storage and trigger circuitry. On command, the energy of the capacitor bank is discharged into a coil wound around the launch chamber. The 3 stages power the 3 coils in sequence. The high current flows through the coils, building a strong magnetic field. By sequencing the 3 stages, the region of the peak field shifts down the length of the launcher, continuously accelerating the payload to its target of 20 feet per second.
To control the sequencing of the launcher, we utilized a commercially available Arduino microcontroller. This allows us to use common development software to easily adjust the launch sequencing. Arduino also allows us additional data logging used to validate the simulated data. 6 channels of high-speed analog to digital conversion allows an accurate measure of each stage's individual current and voltage waveforms. A high-voltage charging circuit was also designed. This allows us to utilize common wall outlets to charge the capacitor banks within 60 seconds. The converter features an isolation transformer, protective fusing, and auxiliary power regulators before the main DC to DC converter stage raises the capacitors to the target voltage.
Preliminary design studies were performed to determine allowable configuration of stage coils. Using MATLAB and ANSYS Maxwell, an initial target was chosen. A convergence study was performed as well to iterate the simulation mesh size and time step in order to efficiently use compute resources while producing usable data. The final ANSYS simulation tracks field strength, force, position, and velocity of the payload. The software allowed us to step through and simulate thousands of variations of starting condition, sequence timing, and other parameters. This simulation provides a visual plot of magnetic field strength during launch. The coils are the white rectangles, and the iron slug pushing the payload is the moving square. Over the course of a few dozen milliseconds, the payload is thrown forward to 21 feet per second with a peak of 270 foot-pounds force. The most complicated interaction of the design can be seen in this. The steel launcher acts like a large transformer core, creating complex coupling of the rising and falling field strengths between the stages. The weakening field is still forceful enough to pull the iron slug back into the launcher while the payload continues out into the environment. Careful iteration of the design is required to minimize the suckback effect for maximum efficiency.
Our results indicate that this design provides the minimum viable route to a functioning depth-rated electromagnetic launcher. Refinement of the hardware and sequencing can increase efficiency and payload capacity. Further, separate studies can be conducted to measure the radiated electromagnetic interference both inside and around the launcher, and design improvements can minimize the effect on surrounding electrical equipment.
Thank you for your interest in our project. We found it rewarding and believe that it shows promise for future projects. Please feel free to contact us with any questions you may have.